Alright, I am so excited to bring you guys this video today. We're going to try something new. I just bought an iPad, so I'm going to use it as a virtual whiteboard, and hopefully this will improve my production quality. You guys can be able to see things on a bigger screen, be able to get some better visuals. So alright, yeah, let's try this out. So let me know what you guys think about it. Alright, so okay, don't look at this code yet, but okay, I'll go through the code later. Let's first talk about the problem. So we're going to look at Leetcode 1066 Campus Bikes 2. If you've already done Campus Bikes 1, you know that the first part, we only had to do a greedy solution. So basically, in the first part, it wanted you have some workers, you have some bikes, you want to pair each worker with a bike, and you want to pair the workers. So basically you go through and find the distances between each worker, each bike, and then you greedily just pair them based on who's closest to what, right? So in this case it would be worker 1 goes to bike 0 and worker 0 goes to bike 1 because worker 1 is closest to this, and then you pair worker 0 with bike 1. So that was all completely greedy. In this problem, it's asking us to return the minimum possible sum of the total assigned distances, right? So basically that means let's see what the total distance would be if we followed the same approach from part 1. So part 1, you would just assign worker 1 to bike 0. So what's that distance? That's a distance of 2 blocks. And then worker 0 with bike 1, that's 1, 2, 3, 4, 5, 6. So that's 2 plus 6. That's a total of 8 units of distance. But it says that the best possible distance is 6. So how did they get 6? Well, they paired worker 0 with bike 0 and worker 1 with bike 1, right? So worker 0 to bike 0 is 1, 2, 3 units. Worker 1 is 1, 2, 3 units to bike 1. So that's a total distance of 6. So ideally you want to minimize your total distance, your total combined distance for all the different assignments. So the only way to do that is actually to try all the different combinations. So that's why this problem, they have way less workers. I think in the first problem they had like 100 or something for N and M. In this problem it's only 10. So you can see how this problem, the time complexity is insane if you do it brute force. I mean, regardless of brute force, it's still going to be a pretty costly problem. So let me show you the different. Let me show you why the time complexity is so high. So let's go to the whiteboard and let's show you how I kind of visualize this in my head. So let's say we have like a set of workers. So we have workers 0, 1, 2, 3, and then we have a bunch of bikes. We have a set of bikes like 0, 1, 2, 3 for bikes. So we'll kind of just go through all the different workers from worker 0 all the way to 3. We'll kind of just sweep through like this, and for each worker can choose either this one, this one, this one, this one, or this one. Any of these bikes that aren't taken yet. So right, so worker 0 could take 1, 2, 3, 4 bikes. So this one, you have 4 different paths here, and then this worker can take, let's say worker 0 took bike 2, so then we go to the next iteration. So for the next worker 1 can choose from any of these 3 remaining bikes, right? So it has 1, 2, 3 choices, and then worker 2, we go to the next bike. Okay, let's just say worker 1 chose this bike, then we go to the next worker 2. Worker 2 can choose from any of the 2 remaining bikes, so he chooses another 2, and then we let's say he chooses 1, then we go to the next worker, the last worker, and this last worker just gets assigned the final bike, right? So we can see that this one had 4, 3, 2, 1. So this is basically n times n minus 1 times n minus 2, blah blah blah, all the way down to n minus 1. This is n factorial time complexity. So this is going to take a long time to do. So let's see where dynamic programming comes in, and where are the subproblems. What are the subproblems that we can get out of this? Okay, so let's see the different subproblems that we have. Sorry for that. Okay, so the different subproblems that we have, let's just say same examples. We have workers 1, 2, 3, 0, 1, 2, 3. We have bikes 0, 1, 2, 3. So let's say we assign this worker bike 1, bike 0, bike 2, and then we come to this. Okay, so let's show you all the different states, right? So we have 1, 2. So let's say in an alternate path, you know, we could have assigned this guy 2, this guy 0, this guy 1, right? So we've processed these first 3, and they've come to the same state, right? Like this last guy has the same exact remaining bikes to choose from, and you know, basically these two subproblems are both gonna have the same answer coming from this 3, right? So remember, if you remember in like a DFS, you know, the bottom stuff, it kind of bubbles up in a DFS. The bottom, the leaves kind of solve their subproblem first, and then it bubbles it up to the, you know, previous one, and then this stuff gets calculated, and then it bubbles the answer back up to the, you know, previous one. So that's why this 3 would get calculated first. This subproblem for 3 would get calculated first. It would pass it back to here. But these two are in the same state, right? We've used up the same exact, you know, 0, 1, and 2 bikes. So that's why these two would be repeating this subproblem for 3. So we can, you know, even another case where we'll be repeating a subproblem is if we assign this one 0. If we assign this one 0, assign this one 1, assign this one 2, right? So you can see that there's a bunch of different overlapping subproblems, and that's why we use DP. So what's the DP that we're going to take advantage of? So we're going to basically keep track of which, so basically we're going to go through the workers again, like this, one by one. And so basically after worker 0 chooses some bike, then we'll keep track of which bikes he took and which bikes are still remaining. So, you know, some naive way to keep track of which bikes have been used and which bikes haven't been used is you can just use a set of length n, or like some list of length n, and, you know, for bike 0, let's say it was used, bike 1 was not used, bike 2 was not used, right? We can just have a Boolean list and pass through a list every time. But caching a list, you can't hash a list in Python. I'm not sure about other languages, but you'd have to turn this into a tuple first. And this is just so costly, and passing along some list every time is also costly and annoying. So actually there's something called bitmasking, and you might have heard this before, and it might sound pretty overwhelming at first, but let me kind of go into the details and show you how bitmasking is so much more efficient than that first approach with the list. So with the bitmask, what we're trying to achieve is obviously the same thing as the list. We want to keep track of which bikes were used and which bikes were not used. How can we do that with a bitmask? A bitmask is going to be a binary string representation. So let's say we have 4 bikes, right? So we have four bits here, right? So this bit here will represent the 0th bike. This will represent the first bike, second bike, third bike. So 0 means that there is no bike present there, or sorry, it has not been used yet. If this was a 1, that would mean that the 0th bike was used. You know, same thing if this was a 1, then it means that the first bike was used. So how can we keep track of, you know, the different okay, let me back up. So first, let's say that we have some existing bitmask that we're passing into the current state. So let's say we're on worker 1 or whatever, and the first guy picked bike 1. So right, so that's what this state is representing. You know, we've already picked the first bike, and we have these other 3 bikes remaining to choose from, right? So we're at worker 1. How do we know which bikes were chosen, and how do we, like, yeah, so how do we determine which bikes are valid to choose from? You know, it would be kind of cost effective if we went through and iterated through every digit of this binary. You know, first of all, this binary is represented as an int. Whatever, just don't worry about that. So basically just think of this as a binary. We'd have to iterate through each digit in the binary, so that would be an O of n operation, so that'd be cost inefficient as well. A way to do it with bitwise operations, which is really quick, is to kind of, we'll use the ampersand, and we'll use a pipe. So the ampersand is the bitwise and, this pipe is the bitwise or. So let me show you guys what I mean by this. Let me grab a sip of water. Sheesh. Okay, so we've taken the first bike. So let's say we're going to be iterating through, you know, for each of these workers, each of these is basically a recursive call, right? We're going through each one as a recursive call, and inside each recursive call, right, like this, right? So we have the worker index. So we're starting from worker 0, and then each DFS call is going to, increment the worker index. So we're kind of just going through and incrementing the worker index every time until we hit the end. But inside each recursive call, we're also doing a for loop. We're going to loop through all the bikes, right? So let's see this. So for B in bikes, so for each worker, we're going to be doing this for loop. And then so basically we're going to be checking if this bike B if it has already been used. How do we check if it's already been used without having to iterate through all these digits, right? What you can do is use the ampersand. So this ampersand is essentially, so what's going to happen is, let's say this bike, so we're iterating through bikes, 0, 1, 2, 3. So let's say we start on the 0th bike here. And so what happens is that 0th bike is going to be represented as it's going to be represented with the string of 0, 0, 0, 1. Right, because this bike is in the 0th position. This string right here, this binary masking, represents that we want to take the bike at index 0. If we were iterating through and we iterated to the second index, then this string would look like it would look like 0, 0, 0, sorry, 0, 1, 0, 0, right? This is the 0th index, first index, second index. This binary string represents we want to take the second bike. So let's say we want to take the second bike, right? So how do we check from the current bitmask, right? This bitmask here is the one that's getting passed in every time in our recursive call, right? We have this recursive call, and we're passing in some bitmask, which represents the bikes that we've already taken and which bikes we haven't taken yet. Right, so let's say hypothetically this is our masking for this recursive call. So how do we go in and compare this mask with this current mask that we want to take from, right? This, like I said, this mask represents that we want to take bike 2. So basically, we can see that bike 2 was not taken in our parameter mask, right? There's a 0 here, so it wasn't taken. So what we can do is we can use an ampersand to compare these two binaries, right? 0, 0, 1, 0 and 0, 1, 0, 0. What the ampersand will do is it will take the AND of these two values, right? The AND of 0 and 0 is 0. The AND of 0 and 1 is 0. The AND of 1, 0 is 0. The AND of 0, 0 is 0, right? So these two ANDed together gave us 0, 0, 0, 0. So that means that if there was nothing, if there was no overlap, if this was 1 instead, if this position 2 was taken, let's say this was taken over here, right, then these two 1s would have produced a 1 here. So this is not equal to 0 anymore, right? This is not equal to 0. So when it's not equal to 0, that means that this bike has already been used. If it is 0, that means this bike hasn't been used. So basically what we're going to be checking is just, we're just going to be checking if, let me go back to the code, we're going to be checking if this mask ANDed together with this right here, I, or 1 left shifted by I. Oh yeah, so I forgot to explain the 1 left shift I. So basically what this means is let's say we were looking at bike 2, right? 0, 1, 0, 0. To get this binary, what we had to do was we had to take a 1. So a 1 is represented as 0, 0, 1 in binary. And we left shifted this 1 2 spots over here. That's how we got this 0, 1, 0, 0, right? So this B, the bike B, has a value of 2, an integer value of 2, right? So if we left shift it by 2 values, so then we're going to be representing this binary 0, 1, 0, 0. So that's what we have here. So if we AND together this original parameter binary string with this current binary string, which is the one that we want to check if it has been taken or not, then like I said, If it comes out to 0, that means that it has not been taken yet. If it comes out to something other than 0, like 0, 1, 0, 0, that means it has been taken and we can't process that bike, and we have to go to the next bike. So, okay, oh yeah, so also, how do we know? So let's go back and have this example again. So how do we, so that's how we check to see if a bike has already been used. So let's say the bike wasn't used and we want to update our mask to reflect that we're going to use that bike. So let's say, you know, we wanted to use this second bike. So first of all, we check that these two ended together, gave us 0. So that means we're good to go and we're good to use this bike. So now after we've used it, we want to update our mask, right? For the next iteration of the recursive call. We want to tell the next recursive call that this state has been changed, that this bike 2 has in fact been used. So how do we update this 1 and put it into the binary string? You know, right? Because our resulting string, we want it to look like this, right? To represent that we have taken a bike here and we've taken a bike here. So how do we do that? How do we update this string? Well, we can use the OR. We can use the bitwise OR. So what this will do is you can OR these two strings together, right? So 0 ORed with 0 gives us 0. 0 ORed with 1 gives us 1. 1 ORed with 0 gives us 1. 0 ORed with 0 gives us 0, right? So that gave us, you know, now this new binary string representation tells us that we have taken a bike at index 1 and at index 2. Right, this is our new state, and we're going to pass this new state to our next recursive call. So let's kind of just walk through the code. So I've kind of gave my spiel about everything now, and let me kind of just walk through the code at this point. So if you haven't watched my previous videos, please do. That's basically what this cache, I've explained the cache twice already, so please watch that. This is essentially the same thing as using a dictionary to store the results of the different combinations of worker index and mask, but in Python it'll just do it for you. So all the different combinations of worker index / mask will have their own entry in this dictionary, and then the value will be the minimum distance at that state. So basically this is the starting point of the application of the function. We call dfs with worker index 0 and a bitmask of 0, an empty bitmask. So we come into the DFS, and basically our base case is if the worker index is equal to the length of workers, then we should return 0 and stop doing anything. So basically the main core of the logic, which I've explained, is we're going to iterate through all the different bikes, and we're going to check to see if the bike was used already. This condition means that it has been used, so we're going to just continue to the next iteration, to the next bike, and try to use the next bike. If this case was not hit, that means that the current bike we're looking at has not been used yet. So we're going to find the distance from the current worker to that bike, and then assign this current worker to that bike, and then we're going to update the workers. We're going to move forward to the next worker and try to assign the next worker to something. And this is, like I said earlier, this is the OR, and we're going to just insert this 1 into that location in the bitmask to represent that we are taking that bike now. And then at the end, we're going to continuously just update this temp variable, which is basically just going to, right, this DFS call is going to return to us some sort of distance, right? Each DFS call is returning a subproblem, right? Because at the end of this, you can see I'm returning temp. So each DFS call returns some sort of subproblem. You know, once you're here, like I said in the earlier example with the 3, this 3 will return some subproblem back to 2, and then this whole thing will return some subproblem back to 1. This will return, right? So each one is returning some subproblem, and you want to minimize that, right? So you're going to take the minimum between the current temp, right? So like I said, we're trying. So this is basically going through all the different bikes, and we're going to try assigning each worker to each of these 4 different bikes, right? So whichever one gives us the smallest value, we're always going to keep updating that. That's what this temp variable is going to hold. And so at the end, we're going to just return this temp, and it's going to be cached in our cache here. All right. Oh, I'm out of breath. I've lost my voice. Please, I think that's a pretty comprehensive explanation. I tried my best. I tried to use the new technology. Please, if you enjoyed the video, let me know. If you have some complaints about my explanation, please give me some feedback. I'm always receptive, open to hearing some feedback. If you like this style, just let me know. Give me some good comment, good feedback, bad feedback, whatever. Just leave some feedback, and tell me what other problems you want me to do. Also, after this video, I'm going to record another video which does bitmask, so you can solidify your understanding of bitmask in the next upload. So, all right, see you guys in the next upload. Thanks for watching.